Hello, everyone, and welcome to whatever week this is in text mining. This week, we're going over supervised learning. So before I get into the slides and all that fun stuff, I did want to go over the midterm projects, finals, the stuff that I think everyone's a little bit stressed about. So just one quick reminder about late penalties and extensions. If you request an extension more than 24 hours before the due date, so if a project is due Sunday, 11:59 p.m. If you request it before Saturday, 11:59 p.m., I will give you an extension, no questions asked, because you have planned ahead. If you ask me Sunday evening for an extension, I don't give you an extension without a late penalty because you have not planned ahead. That is to say, I know you're human, I'm human. I'm recording this at noon on Monday. I'm a little late too. But we have to plan ahead a little bit. So just ask in advance if you need an extension, and I'm happy to give it. But you also know that my late penalties are really minor. I don't want to penalize you too much, just enough to incentivize you to get things done on time. That being said, some of the questions I'm getting are really, really good. So I am really excited that a lot of you are going. I think a lot of you are challenging yourself and going to the data science track, which I'm very excited about. Surprised in a really good way. I'm very excited that you're trying web scraping, you're doing all these fun things. If you get to a point when web scraping, and if you see my eyes moving, I never know if I'm supposed to look at myself or the webcam. So sorry, I'm a total, I feel like an old person doing Zoom sometimes. If you try web scraping and you get to a decent point, you're at least getting something back, or you're making a good effort and you're not getting the data that you need, send me the code. I prefer the Python file. I only ask for the HTML on actual homework grading, just because I can't see the Python file in Brightspace. But if you email the Python file and tell me what's happening, what error you're getting, or what you're trying to do, I would be happy to help you. One of you did that last week. You planned ahead a little bit. You showed me, hey, I'm doing this, I'm not getting any data back. And I was able to take a few minutes, fix your code for you, and send it, and you now have the code you need. I would consider a lot of the web scraping outside the scope of this class. So I don't expect you to get web scraping 100% correct. I don't expect you to be able to do that completely on your own or anything. So as long as you show me you're making a good effort to get your data, just talk to me. I'm happy to help. But yeah, I just need to see that you've done something, you're putting in a little effort, and then I'd be happy to help. Let's see, what else was I going to tell you? Office hours, no one ever showed up to any of the group office hour sessions I did. So continue to just ask for those as you need them. I'm trying to figure out how to make a scheduling link so you can just schedule whenever you need. If a question is better answered, like you have a coding question, feel free to just send that via email and I can usually help you. Feel free to send definitely your whole code. That helps as much as you can. A full screenshot of whatever error you're getting. And then if you're using a data set that, even if I provided it, please send the data set so that I can run it on my computer. Let's see. Homework. Oh, I'll probably mention this at the end of the video too, but the homework for this week, because I know I overloaded you a little bit last week. I'm sorry. I had the midterm and another homework due the same week as 4th of July. That was just mean. So I'm giving you a week off this week. Your homework will be due not the 14th, but the next Sunday. Definitely start early if you don't want to be in a mad rush to finish it. Especially because this can be used as part of your final project. Every homework from here on out, just literally take it and use it as part of your final project. But yeah, I'm giving you a little extra time to do that because that was not kind of me. I think that's it. So let's go ahead and dive in. All right. I'm going to stop my video too. I have so many screens. I don't want you to just stare at the side of my head. Okay. So supervised learning. When we talk about supervised learning, I am talking about predictive analytics. I'm talking about machine learning. I'm talking about artificial intelligence. I say supervised learning because some people in the data science community are very particular about what phrases we use. So this is just a very specific term, but in general, we're all talking about the same thing. We're talking about using historical data to predict future data. Or occasionally, even if we don't have future data, we're using historical data to figure out how does the data work? Why is something kind of going a certain way? So some learning objectives, we're going to describe alternative measures for model accuracy and the context in which each is appropriate. We're going to, oh, nope, we're not doing number 2. That was my other class. And then we're going to apply supervised machine learning methods using the numeric representation of text. So this entire term, we've been taking text and we've been creating a data set. Now we're going to take that data set and create a predictive model out of it. Because as we've been creating these data sets, we like numbers, so we made text into numbers. Now let's do some of the cool things you've learned before in predictive modeling. So quick refresher on predictive analytics. Again, when I say AI, predictive analytics, machine learning, modeling, I'm taking past historical data. I already have the data in hand. I either want to fill in some gaps, whether it's like missing data, I don't know some of the fields, or I want to predict future data, or I don't know the relationship between some data points. I want to fill in those gaps using some sort of algorithm. And when I say algorithm is just a fancy term for a set of rules. Now, some of these rules are very simple. We're going to be using 2 algorithms. One is decision tree, where it's literally based on rules, a lot of times yes or no questions, and that's just how we build our algorithm. And sometimes it's a little bit more complicated. I took out some of the more complicated algorithms. I really want you to focus on the core of this class and not get distracted. But if you go into some of the higher level modeling, sometimes the rules are really hard to interpret. I think like neural networks. We can't really describe what's going on inside of there. That's why they're a little harder to use. We can't go to our boss and say, hey, this is why the model says we should do this. But they're still built on a set of rules. So when we talk about predictive analytics and machine learning, we're trying to ask what will happen. So what will happen in the future, or if I had all of the data, what should have been here? So supervised machine learning, which we're talking about this week, the data is labeled. And that means not just the column names are labeled, but that means whatever we're trying to predict is labeled within the data set. So we are aiming to predict something specific. In unsupervised machine learning, we are looking for patterns in the data. We might not know exactly what patterns we're looking for, what we might think we will find. Sometimes we do, sometimes we don't. But it's unsupervised because we're letting the computer kind of say, what do you find? Unsupervised learning, we're going to go over next week. Supervised machine learning is what we're covering this week. So an example of supervised machine learning, if I give you a data set, so this is like a little subset of a data set, I've got an ID, age, gender, and if someone bought or they did not buy a product. So in supervised machine learning, I might give you this data set and say, based on this, which customers will buy in the future. So you would take this and you would create an algorithm. So you'd create a set of rules and figure out, okay, based on age and gender, how would I figure out if someone would buy or not buy? Excuse me. That summer cold, it just never goes away. In unsupervised machine learning, we might say which customers are most similar. Or if we look at the customers that do buy, what makes them, what puts them together? What's that dividing link besides the fact that they all bought this product? Oh, okay. I thought I was gonna cough again. Okay. So in this one, we have a specific thing that we're trying to predict. Is someone going to buy or not buy? We have labeled data, which means we already have data here that says if someone bought or did not buy in the past, and we're going to predict it. In this one, we're just trying to figure out what patterns exist. So even though we have the same column, because we're not trying to predict if they're going to buy, we're trying to figure out a pattern within it, which there is no column for pattern. There is no like grouping of these customers. That's what makes it unsupervised. There are two types of supervised learning, classification and regression. This week, we are solely focused on classification, but I've read over some of your midterm projects and I do see some of you are looking at regression, so I'm going to go over that as well. So in classification, we're asking what category is X? So male or female, which is a bad example. We're never really trying to predict if something is male or female. Upper, middle, or lower class. Is someone going to buy or not buy? A really common one in sales and marketing is churn modeling. So is a customer going to stay with the company they're at now, or are they looking to leave? When I worked at Sprint, which is now part of T-Mobile, I worked on churn modeling quite a bit, and we were always asking that question. So if I look at a data set of people that previously left Sprint and customers who stayed long-term. So for example, I look at customers from June of 2023, and then I have them labeled of, are they still here? So they did not churn, or they left, so they did churn. How can I figure out when I get new customers, are they going to churn or not? It's classification because I'm predicting a category, churn or not churn. And it's supervised learning because I have a data set that is labeled with churn or not churn based on previous historical data, and I'm predicting something specific. The other type of supervised learning is regression. Now, you might remember linear regression, logistic regression from some of your lower level stats courses. These are sometimes not considered part of machine learning, which I just call, that's why I just say supervised learning. And it's because we're really not predicting something specific. We are talking about like a range. We're trying to understand a typical value. I still group them all together into supervised learning. We're using historical data to predict a future value. But in regression, we're asking what value is X? So what will gas prices be a month from now? What is someone's age based on their characteristics? How many things are they going to purchase based on how they clicked around on a website? So very common types of supervised learning. In classification, we're asking about a category. So if you look at a column, that's typically if you have maybe a string variable. So you have buy, not buy, churn, not churn, real or fake, and regression, what value. So you're looking at numerical values. Now you can turn a regression problem into a classification problem. So for example, gas prices, you could turn that into a classification problem by binning your data set. And I'm going to say a gas price. I have not filled up at the pump in a very long time, so don't judge the number I'm about to throw out. But is gas going to be above or below $3.30? So in that case, I'm still predicting a value, but since I'm guessing or I'm predicting if it's going to be above or below, that makes it a classification because it's a category. So classification is what we're focused on primarily. So again, it assumes we have labeled data. So we need historical data, some sort of data that has labels on what we're trying to predict. There are many, many types of algorithms that all optimize differently. They all operate differently. We are only focused on decision trees and random forests for the scope of this class. If you want to look into more, I'm happy to provide you some code. I have some for quite a few different models. But for this class, I really want to focus on the text portion and really focusing on what problem are you trying to solve. The other piece we are looking at are the performance measures to choose from. So traditionally we look at accuracy, but we also want to look at things like precision and really looking deeper at not just did we get this label correct, but what happens if we didn't? What could go wrong if we label something incorrectly? It may require additional pre-processing. So depending on our problem, we might have some extra things we're going to throw into our data cleansing. And then we might need to scale things. So I gave this example of likes versus term counts. If we are predicting if something is real or fake on social media, and say we have the text and we also have the number of likes the account or the post has, if we have term counts, it's going to be 0, 1, 2, and so on. So really small numbers. And if we have likes, that could be between 0 and maybe a few million. So we might scale things to make it more normalized because we're data people. We don't like things to be in two very, very different scales. Our algorithms operate more effectively and more mathematically correctly when we have things on the same type of scale. So just kind of keep that in mind. With this video and the code and all the orange stuff I'm giving you, we're not looking at scale at all. I've taken a lot of the extra information out because I just want to keep the end of this class very focused, but just kind of know that that's out there. When we're looking at performance measures, and hopefully you went through this in predictive modeling, but when we look at classification problems, we want to know if something is, and we're going to use true, or we're going to use positive and negative for this. If something is positive and we predict it is positive, that means it's a true positive. We predicted it would be positive. It's accurate. If we predicted positive and it was actually negative, that's a false positive. So honestly, COVID was obviously horrible, but it was really, really great for statistics understanding because people are starting to understand a false positive, true positive, false negative, all of those a lot easier because you have kind of something in hand. So false negatives are ones where we think it's actually negative, but it's positive. True negatives, we predicted correctly that it's negative. False positives, we predicted positive, it's actually negative. Now we know accuracy. Hopefully we know accuracy is going to be our correct predictions over all of our predictions. So just the percentage of the ones we got correct. There are other measures as well. So precision is our true positives over the ones that we predicted were positive. So true positive over true positive plus false positive. We're looking at this when we want to understand oh, sorry. We're looking at this when we want to understand specifically more about predicting positives. We're really focused on making sure that only the ones that are positive are being called out. So say, for example, trying to think of a good one. Oh, so like in sales, this is a big one. In sales, we typically call out a few specific clients that are very likely to buy. And in those cases, we spend a lot of money, a lot of time on those clients. When we are looking at just overall accuracy, we're going to look at everyone, even if we predicted that they were not going to be a big client. We didn't spend as much money on them, but they were. In that case, if you look back, that's kind of like, oh, okay, we got it wrong, but it's okay. In this case, we're looking at those false positives, because if you think about it, all the positives, so we predicted that they would be these big, important clients. These false positives are one that we spent a lot of time and money on, and they didn't actually result in anything. So that's a lot of missed opportunity. We could have been spending time with other clients, maybe a lot of wasted effort. Maybe we didn't know that client well enough. So that precision would better tell us how did we spend our time and money? Versus recall, which is also, it's including that false negative. So it's looking at those missed opportunities. Let's see. What I want to, oh, let's do cancer for this one. So true positives and also false negatives. So if we're testing for cancer, the worst case scenario is that we miss someone with cancer. So even if yes, it's bad if we tell someone that they have cancer and they don't, but we can at least have some extra testing and then say, oh, actually, that was negative. You're good to go now. Yes, it was extra money and time and stress, but at least this person is now for sure that they do not have cancer. When we're looking at recall, we can be more specific in how we are basically penalizing ourselves for getting false negatives. So saying someone is cancer-free when they really do have cancer. So you see the difference in this. It's in basically our missed opportunities, or in the case of healthcare, we don't want to say missed opportunities, but things like risk. So where is our risk? So where are we really trying to optimize? Because in predictive modeling, as much as we want to be 100% accurate, that's never going to happen. And honestly, we will see later on in the data set that I give you, if you are 100% accurate, something's probably wrong with your data set, because something's always going to be a little bit wrong. We're never going to be 100% correct. When we are, that's called overfitting. It means we are so in tune with our test data set that maybe the data set is just so fake it doesn't work, or maybe we have overfit like those skinny jeans that they are just so overfit to your body that if you change anything, they just don't fit at all anymore. That would be this model. If it's overfit, it works really, really well for that one data set. But as soon as any one thing changes, you get one new record, one person changes slightly, the entire model stops working. So some applications in text mining. We could look at an email and predict whether the email is legitimate or spam. So that's how most email providers actually work nowadays. They use machine learning in the background. They read the text of your email just to, they're not reading it, hopefully. They're looking to see what kinds of words are used, and they can predict if it's legitimate or spam. Based on financial filings, predict which companies are most at risk for declaring bankruptcy. I've seen a few applications of this. It's pretty neat. I never remember the document, but there's some sort of document that companies file to the Federal, the Federal Reserve, I think. Anyway, they file this document to kind of talk about their financial state and all of this. And if a company is going to go bankrupt, most of the time they're not going to blatantly say we're in dire financial state. So you can actually use text mining to find the words that they will use instead and predict if they're going to go bankrupt. I had a student look at all of Taylor Swift lyrics, and for any given song lyric, predict which era of Taylor Swift the lyric belongs to, kind of based on the words she's using and the type, like the maturity of some of the lyrics. That was pretty neat. And obviously much, much more. The applications I've used, Sprint, it was the churn modeling. Oh, and then I did a lot with the sentiment analysis plus churn modeling. So taking sentiment analysis plus applications of their cell phone plan and things, and like adding all of that together into predictive model to see who's going to leave Sprint or stay. So pretty neat. Oh, I forgot the other one. It was at, I guess you all wouldn't know, it's in Kansas City. It's a company called DST, now SS&C financial company. But we would get emails in and we'd have to forward them on to different teams. Very tedious. It was a team of like 7 people manually reading emails and forwarding them on. So what I would do is I created an algorithm that would read the email and based on keywords, figure out which team the email should go to, which really could be an Outlook rules engine. But with text mining, it was like 90% accurate, which was better than the people reading the emails. So that was pretty cool. We found out like certain words and phrases meant it would go to certain teams over others. So lots and lots of different applications in text mining. A lot of you are doing political ones, which if you have the stomach for it in this election year, go for it. Speaking of that, please, if you are eligible to vote, please register to vote. Again, algorithms that used this week are decision trees and random forests. I've added a few explainer videos that I like to Brightspace, just to go over those. All right, and that is it for the lecture part. I am just going to quickly show you the code in orange right now, because this is pretty short this week. I kept them pretty, yeah, pretty standard. So for anyone that wants to use orange, this is what the end goal. There is a slide deck on Brightspace that goes step by step with screenshots of what to do. But you're essentially taking data, turn it into a corpus, pre-processing your text, getting your bag of words, which is just the words you're going to use for your model, selecting your columns, and then you're going to test and score. This is the only weird part. You go from columns to test and score, and then you add your models. And then at the end, you get your confusion matrix, which is how you look at accuracy and precision and all those fun things. And then predictions. Let me see if this is still up and open. Oh, it is good. So this is what it looks like. It's like the bag of words. Here's all of the words that are being used. We're using a real and fake news data set this week. I apologize for any bad words in it. When it's fake news, sometimes it's really bad. And then when we get the models, this is what you're going to see. So you're going to see like the random forest is 95% accurate and the decision tree is 90.8% accurate. And I left a link in the slides for the other items. So pretty neat. And then the code part, let's see where that is. Oh, here we go. So this one is another one that's pretty straightforward. Just make sure you're using the correct data set. And then data prep. And we see our fake and real news. So we've got about a 50-50 split. And then here I show you just how to implement the models. The code I'm giving you, I tried to give you code that you could reuse as often as you want. So really, really simple code where we define X and Y, X being the features and Y being the label, so what we're trying to predict. And then we get all this. So a lot shorter than most weeks. So spend some time with this. I took out a lot of the more technical details of a lot of the models. There's lots of other further reading if you want to look into it. But yeah, with this, you can see it's like this one predicted it was real, but if you look at it, it's actually not correct. It's fake. And I can almost guarantee exactly why it did that. Yes, it talked about Hillary Clinton and the IRS, which almost is always fake anytime you see stuff like this. But it also said rooters, which if you look through the rest of the data set, anytime it says this, it's almost always a real news story. It's pretty interesting. So your homework this week, hopefully you have fun with it. You are taking that data set and you are making your two models based on first the title and then the text. So 4 models in general. And then you're basically going to say, if you were a social media company, how would you go about picking which model was going to be used and why, and what are some ethical considerations? So with that, okay, I'm back. So hopefully this week goes pretty smoothly, but feel free to reach out to me if you have any questions at all. I'm pretty fast at responding, and if I'm not available to like fix code or anything, I still respond at least and tell you, hey, I can get back to you tomorrow. So don't hesitate to reach out and have a great week. Thanks. Bye.